The multiple integral is a generalization of the definite integral to functions of more than one real variable, for example, f or f. Integrals of a function of two variables over a region in R2 are called double integrals, and integrals of a function of three variables over a region of R3 are called triple integrals. Introduction. Just as the definite integral of a positive function of one variable represents the area of the region between the graph of the function and the x-axis, the double integral of a positive function of two variables represents the volume of the region between the surface defined by the function and the plane which contains its domain, equals 1 over the above-mentioned region between the surface and the plane. If there are more variables, a multiple integral will yield hypervolumes of multidimensional functions. Multiple integration of a function in n variables, f over a domain D, is most commonly represented by nested integral signs in the reverse order of execution, followed by the function and integrand arguments in proper order. The domain of integration is either represented symbolically for every argument over each integral sign, or is abbreviated by a variable at the rightmost integral sign. Since the concept of an antiderivative is only defined for functions of a single real variable, the usual definition of the indefinite integral does not immediately extend to the multiple integral. Mathematical definition. For n greater than 1, consider a so-called half-open, n-dimensional hyperrectangular domain T, defined as partition each interval aj, bj, into a finite family ij of non-overlapping subintervals ij alpha, with each subinterval closed at the left end and open at the right end. Then the finite family of subrectangles C given by is a partition of T, that is, the subrectangles CK are non-overlapping and their union is T. Let f, Tr be a function defined on T. Consider a partition C of T as defined above, such that C is a family of m subrectangles Cm, and we can approximate the total th-dimensional volume bounded below by the n-dimensional hyperrectangle T and above by the n-dimensional graph of f with the following Riemann sum, where pk is a point in ck and m is the product of the lengths of the intervals whose Cartesian product is ck, otherwise known as the measure of ck. The diameter of a subrectangle ck is the largest of the lengths of the intervals whose Cartesian product is ck. The diameter of a given partition of T is defined as the largest of the diameters of the subrectangles in the partition. Intuitively, as the diameter of the partition C is restricted smaller and smaller, the number of subrectangles M gets larger, and the measure M of each subrectangle grows smaller. The function f is said to be Riemann integrable if the limit exists, where the limit is taken over all possible partitions of T of diameter at most delta. If f is Riemann integrable, S is called the Riemann integral of f over T and is denoted frequently. This notation is abbreviated as where x represents the n-tuple and dnx is the n-dimensional volume differential. The Riemann integral of a function defined over an arbitrary bounded n-dimensional set can be defined by extending that function to a function defined over a half-open rectangle whose values are 0 outside the domain of the original function. Then the integral of the original function over the original domain is defined to be the integral of the extended function over its rectangular domain, if it exists. In what follows, the Riemann integral in n dimensions will be called the multiple integral. Properties. Multiple integrals have many properties common to those of integrals of functions of one variable. One important property of multiple integrals is that the value of an integral is independent of the order of integrands under certain conditions. This property is popularly known as Fubini's theorem. Particular cases. In the case of Tr2, the integral is the double integral of f on T, and if Tr3, the integral is the triple integral of f on T. Notice that, by convention, the double integral has two integral signs. and the triple integral has 3. This is a notational convention which is convenient when computing a multiple integral as an iterated integral, as shown later in this article. Methods of integration. The resolution of problems with multiple integrals consists, in most of cases, of finding a way to reduce the multiple integral to an iterated integral, a series of integrals of one variable, each being directly solvable. For continuous functions, this is justified by Fubini's theorem. Sometimes, it is possible to obtain the result of the integration by direct examination without any calculations. The following are some simple methods of integration. Integrating constant functions when the integrand is a constant function C. The integral is equal to the product of C and the measure of the domain of integration. If C equals 1 and the domain is a subregion of R2, the integral gives the area of the region, while if the domain is a subregion of R3, the integral gives the volume of the region. Example: let f equals 2, and in which case, since by definition we have use of symmetry when the domain of integration is symmetric about the origin with respect to at least one of the variables of integration and the integrand is odd with respect to this variable, the integral is equal to 0, as the integrals over the two halves of the domain have the same absolute value but opposite signs. When the integrand is even with respect to this variable, the integral is equal to twice the integral over one half of the domain, as the integrals over the two halves of the domain are equal. Example 1. Consider the function integrated over the domain a disk with radius 1 centered at the origin with the boundary included. Using the linearity property, the integral can be decomposed into 3 pieces. The function 2 sin is an odd function in the variable x and the disk T is symmetric with respect to the y-axis, so the value of the first integral is 0. Similarly, the function 3y3 is an odd function of y, and T is symmetric with respect to the x-axis, and so the only contribution to the final result is that of the third integral. Therefore the original integral is equal to the area of the disk times 5, or 5 pi. Example 2. Consider the function f equals x(exp) in as integration region the sphere with radius 2 centered at the origin. The ball is symmetric about all 3 axes, but it is sufficient to integrate with respect to x-axis to show that the integral is 0, because the function is an odd function of that variable. Normal domains on R2. This method is applicable to any domain D for which the projection of D onto either the x-axis or the y-axis is bounded by the two values, A and B. Any line perpendicular to this axis that passes between these two values intersects the domain in an interval whose endpoints are given by the graphs of two functions, alpha and beta. In all cases, the function to be integrated must be continuous on the domain x-axis if the domain D is normal with respect to the x-axis, and f dr is a continuous function, then alpha and beta are the two functions that determine D. Then, y-axis if D is normal with respect to the y-axis and f dr is a continuous function, then alpha and beta are the two functions that determine D. Then, example, consider the region. Calculate this domain is normal with respect to both the x and y-axis. To apply the formulae it is required to find the functions that determine D and the intervals over which these are defined. In this case the two functions are, while the interval is given by the intersections of the functions with x equals 0, so the interval is a, b equals 0, 1. It is now possible to apply the formula. The remaining operations consist of applying the basic techniques of integration. If we choose normality with respect to the y-axis, we could calculate and obtain the same value. Normal domains on R3. The extension of these formulae to triple integrals should be apparent. If T is a domain that is normal with respect to the xy plane and determined by the functions alpha and beta, then change of variables. The limits of integration are often not easily interchangeable. One makes a change of variables to rewrite the integral in a more comfortable region, which can be described in simpler formulae. To do so, the function must be adapted to the new coordinates. Example 1a. The function is, if one adopts this substitution, therefore one obtains the new function. Similarly for the domain, because it is delimited by the original variables that were transformed before, the differentials dx and dy transform via the absolute value of the determinant of the Jacobian matrix containing the partial derivatives of the transformations regarding the new variable. There exist three main kinds of changes of variable. However, more general substitutions can be made using the same principle. Polar coordinates in R2. If the domain has a circular symmetry and the function has some particular characteristics, you can apply the transformation to polar coordinates, which means that the generic points P in Cartesian coordinates switch to their respective points in polar coordinates. That allows one to change the shape of the domain and simplify the operations. The fundamental relation to make the transformation is the following. Example 2a. The function is, and applying the transformation one obtains example 2b. The function is, in this case, 1 has. Using the Pythagorean trigonometric identity, the transformation of the domain is made by defining the radius, crown length, and the amplitude of the described angle to define the ρ, phi intervals starting from x. Example 2c. The domain is, that is a circumference of radius 2. It's evident that the covered angle is the circle angle, so phi varies from 0 to 2 pi, while the crown radius varies from 0 to 2. Example 2d. The domain is, that is the circular crown in the positive y-half plane. Phi describes a plane angle, while ρ varies from 2 to 3. Therefore the transformed domain will be the following rectangle. The Jacobian determinant of that transformation is the following, which has been obtained by inserting the partial derivatives of x equals ρ cos, y equals ρ sin in the first column respect to ρ and in the second respect to phi. So the dx dy differentials in this transformation becomes ρ d phi. Once the function is transformed and the domain evaluated, it is possible to define the formula for the change of variables in polar coordinates. Phi is valid in the 0, 2 pi interval, while ρ, which is a measure of a length, can only have positive values. Example 2e. The function is f equals x and the domain is the same as in example 2d. From the previous analysis of d we know the intervals of ρ and of phi. Now let's change the function. Finally, let's apply the integration formula. Once the intervals are known, you have cylindrical coordinates in R3. The integration on domains with a circular base can be made by the passage in cylindrical coordinates. The transformation of the function is made by the following relation. The domain transformation can be graphically attained, because only the shape of the base varies, while the height follows the shape of the starting region. Example 3a. The region is, if the transformation is applied, this region is obtained. Because the z component is unvaried during the transformation, the dx dy dz differentials vary as in the passage in polar coordinates. Therefore, they become ρ d phi dz. Finally, it is possible to apply the final formula to cylindrical coordinates. This method is convenient in case of cylindrical or conical domains or in regions where it is easy to individuate the z interval and even transform the circular base and the function. Example 3b. The function is, and as integration domain this cylinder. The transformation of d in cylindrical coordinates is the following. While the function becomes finally one can apply the integration formula. Developing the formula, you have spherical coordinates in R3. Some domains have a spherical symmetry, so it's possible to specify the coordinates of every point of the integration region by 2 angles and 1 distance. It's possible to use therefore the passage in spherical coordinates. The function is transformed by this relation. Points on z-axis do not have a precise characterization in spherical coordinates, so theta can vary between 0 to 2 pi. The better integration domain for this passage is obviously the sphere. Example 4a. The domain is, applying the transformation you get this region. The Jacobian determinant of this transformation is the following. The dx dy dz differentials therefore are transformed to ρ2 sin d rho d theta d phi. This yields the final integration formula. It's better to use this method in case of spherical domains and in case of functions that can be easily simplified by the first fundamental relation of trigonometry, extended in R3. In other cases it can be better to use cylindrical coordinates. The extra and come from the Jacobian. In the following examples the roles of phi and theta have been reversed. Example 4b. D is the same region as in example 4a and is the function to integrate. Its transformation is very easy. While we know the intervals of the transformed region T from D, let's therefore apply the integrations formula, and, developing, we get example 4c. The domain D is the ball with center in the origin and radius 3a, and is the function to integrate. Looking at the domain, it seems convenient to adopt the passage in spherical coordinates. In fact, the intervals of the variables that delimit the new T region are obviously. However, applying the transformation, we get. Applying the formula for integration we would obtain, which is very hard to solve. This problem will be solved by using the passage in cylindrical coordinates. The new t intervals of the z interval has been obtained by dividing the ball in two hemispheres simply by solving the inequality from the formula of d. The new function is simply ρ2. Applying the integration formula, then we get, thanks to the passage in cylindrical coordinates, it was possible to reduce the triple integral to an easier one-variable integral. See also the differential volume entry in nabla in cylindrical and spherical coordinates. Examples. Double integral. Let us assume that we wish to integrate a multivariable function f over a region A. From this we formulate the double integral. The inner integral is performed first, integrating with respect to x and taking y as a constant, as it is not the variable of integration. The result of this integral, which is a function depending only on y, is then integrated with respect to y. We then integrate the result with respect to y. Observe that the order of integration is sometimes interchangeable. The instances where the order is interchangeable is determined by Fubini's theorem. Computing a volume using the methods previously described, it is possible to calculate the volumes of some common solids. Cylinder. The volume of a cylinder with height h and circular base of radius r can be calculated by integrating the constant function h over the circular base, using polar coordinates. This is in agreement with the formula. Sphere. The volume of a sphere with radius r can be calculated by integrating the constant function 1 over the sphere, using spherical coordinates. Tetrahedron. The volume of a tetrahedron with its apex at the origin and edges of length L along the x, y and z axes can be calculated by integrating the constant function 1 over the tetrahedron. This is in agreement with the formula multiple improper integral. In case of unbounded domains or functions not bounded near the boundary of the domain, we have to introduce the double improper integral or the triple improper integral. Multiple integrals and iterated integrals. Fubini's theorem states that if the integral is absolutely convergent, then the multiple integral will give the same result as the iterated integral. In particular, this will occur if f is a bounded function and a and b are bounded sets. If the integral is not absolutely convergent, care is needed not to confuse the concepts of multiple integral and iterated integral, especially since the same notation is often used for either concept. The notation means, in some cases, an iterated integral rather than a true double integral. In an iterated integral, the outer integral is the integral with respect to x of the following function of x. A double integral, on the other hand, is defined with respect to area in the xy plane. If the double integral exists, then it is equal to each of the two iterated integrals, and one often computes it by computing either of the iterated integrals. But sometimes the two iterated integrals exist when the double integral does not, and in some such cases the two iterated integrals are different numbers, i.e., one has this as an instance of rearrangement of a conditionally convergent integral. The notation may be used if one wishes to be emphatic about intending a double integral rather than an iterated integral.